Hello, 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 hello. Okay, hello everyone. And today we'll be starting our lecture on network theory, and this is an introductory lecture on network theory. As discussed, will not be covering a lot about what is resistance, what is current, what is voltage, what is Ohm's law. I guess this is something that we are very acquainted with since our 10th and 12th standards. So this is something that I would not be discussing. We directly jump on active and passive elements. And before that, in case you have any issues, you can just go on, ask me on the live chat, and then we can, from there on, we can take it forward. Okay, now assuming that we should directly jump over the topic. Is it fine if I directly start with what are different kinds of elements? So, beginning with what are active and passive elements. An element is said to be active if it is able to deliver energy to an external network to which it is connected, and in case it is not, then it would be a passive element. Let me give an example. See, what we understand with active elements would be anything which has anything which is capable of delivering. What would that be? um, a current source, a voltage source, and in many of the cases, it is also said transistors and other nonlinear devices which are able to amplify a signal are also classified under the head of active elements. So, if any element in a circuitry has the capability to enhance a signal or probably deliver energy to other rest of the network. I hope you're clear with what are different kinds of sign conventions. Are you? Hmm. I see only two live learners, and I would expect you to be a little more, I would need prompts from your side because it is something which is very, this topic is something which is very basic. And in case you don't respond, it's like I'm talking to a wall. Okay, so let's say we have uh, a network such that this is a generalized network N, and in case the current, the direction of current in this source, or probably in this element is such that it is, you know, it is delivering the network, then such this element would be, this would be a active element. Anything which is delivering a network would be a active element. Similarly, transistors which have the capability of amplifying our signal are also active elements. These are basic definitions, and I don't think like there'll be any doubt when I cover these topics. Passive elements. What would be passive elements? Any element which is, uh, which would not deliver energy, rather which absorbs energy. So such elements intrinsically which have the capability of absorbing uh, energy are passive elements. These would consist of our resistance, inductance, and our inductance, capacitance, and your resistance. The basic passive elements would be such elements, right? Uh, Now again, it is expected, like again, it is assumed that any active element would have the capability to deliver energy for an infinite period of time. So anything, not everything is idealistic, but generally, uh, a power source which is able to deliver for a certain period of time is considered an infinite period of time. Again, assuming the source is ideal in nature, right? In case it is not ideal, then there would be some resistance present in the voltage source or the current source, whatever be the case, and in that case the element that would dissipate energy, right? Now talking about what are linear and non-linear elements, right? So linear, an element is said to be linear if its VI characteristics are straight and are passing through the origin. Otherwise, it is non-linear. Now we say the general equation of a straight line would be y is equals to mx plus c, right? But a linear element uh, with any element with characteristics shown as in this case will not be called a linear element. Why? Because the characteristics are not passing through the origin. So a linear element would essentially be something of this sort, which passes through the origin. Otherwise, even an element whose characteristics it is defined by equation of a straight line will not be a linear element. Am I being clear? Now, again, linear circuits follow the principle of homogeneity, superposition, and reciprocity. With homogeneity, what do you understand? See, if we are give if to a certain network we give a input x1, then the output should be y1, right? And similarly, if we give an input x2, the output should be y2. A homogeneous network would be when the input is x1 plus x2, the output should be.
Am I loud enough now? Like, can you hear me more clearly? So, if the input is x1 plus x2, if the input is x1 plus x2, the output should be the output. The output should be y1 plus y2. And now from here on, you'll understand why I was talking. The a straight line would not work for you. Equation of general equation of straight line would not work for you. Would not be linear. See, okay. So in case your network is defined su- su- such that y1 equals mx, y equals mx plus c. Now, if the input is given as x1, the output y1 would be mx1 plus c. Similarly, if the y input is x2, the output would be mx2 plus c. In both these cases, if we see when input is x1 plus x2, right, the output should be y1 plus y2. Do we see? Uh, can we justify this? So plus 2c, which is not equal to y1 plus y2. This is not equal to y1 plus y2, right? Uh, and so it is not a homogeneous system, and hence it is not linear. A linear system would essentially be homogeneous, reciprocal, and and will follow the principle of superposition. Now, moving on, we have systems which are we have elements which are bilateral and unilateral. Now, what do you understand by a bilateral element and a unilateral element? A element is said to be bilateral if it offers the same impedance for different directions of current through it. Otherwise, it would be linear. It would be unilateral. Now, what is a unilateral element? Elements such as diodes. For example, a diode would allow, when forward biased, would have a very poor very poor resistance. It offers a very low resistance, right? And when it is reverse bias, it provides a uh, huge resistance. It provides a huge resistance, right? It behaves as a open circuit. So when the direction of current changes, or when the applied voltage changes, the current and the direction of current changes, the impedance offered, or probably the nature of the network changes, and such a network would not be bilateral. It is a unilateral network. Now, if we see something as basic as a resistor, right? When you when you apply some voltage to a resistor, say this is your resistor, right? And if we apply a voltage of this sort, the current would flow here in this direction. How would you define R here? R is equals to V by I. Now, in case we have the direction of in case we apply a reverse voltage here, right? The direction of current would be in this. So by general sign convention, if we see the resistance is not changing again, the resistance is unchanged. So such an element where the change in direction of current does not change the nature of its characteristic, then such an element would be a bilateral element, right? Okay. Now, what is a time variant and okay, if we say let's say if if we are like if we are to define so a bilateral or a if we have to define like in case we have a VI graph and we need to understand what is a bilateral or unilateral element and we're provided with a graph. In case you've heard of triac, the characteristic of triac is something of this sort, right? So anything which is symmetric in first and third quadrant is a bilateral element. And if we're not talking about triacs, let's say simple linear elements, let's say we have resistance. Consider this line to be through origin, right? If, um, let me redraw it again. So in case in anything which is in general, you need to understand anything which is passing through the origin and which is symmetric in both first and third quadrant would be a bilateral element. That is, if graphically you are given to identify if an element is bilateral or unilateral, that is how you understand. Again, very clearly, if you find any characteristic anywhere where you find negative concept of negative resistance, what is negative resistance? Tell me. So anywhere where you find the concept of negative resistance, so negative resistance is essentially a feature of active elements. You would not find negative resistance in passive elements. So in any characteristic where you find the ratio of V by I as negative, you can without doubt claim it to be an active element. It cannot be a characteristic of a passive element. Okay. Now, next we'll be taking what is time variant and time invariant system. An element is said to be time invariant if its VI characteristics are constant with respect to time. Just for the sake of hearing a like consider this as just because consider simply as a definition, right? We'll see when the topic when we'll discuss topic in detail. We'll know what is time variant and time invariant system in general, just for the sake of hearing out the definition, you can understand what is a time variant and time invariant system. Anything which changes with time would be time variant. Anything which does not change over time would be time invariant system, right? Now, again, this was something that we discussed yesterday also. What is lumped and a distributed network? Okay, lumped system, any element which is physically present would be a lumped parameter. See, when in case you've heard about what are transmission lines, so transmission lines, the lines which provide power to the which bring electricity to your home. These lines are distributed. These lines are example of distributed parameters. because you don't see a resistance localized to a particular point. For example, in electronics or in the network that you create for observations or probably your experiments, you see the resistance is there are carbon rings for resistors, right? And the resistance is localized to that element itself. But in transmission lines, what we see is the resistance is distributed all over the length. So the resistance is a parameter of a length. So the longer the resistance, the longer the transmission line, the greater would be the resistance. So such parameters where the length, where the resistance or impedance is not localized or is not lumped would be a distributed network. Now, yesterday also I said network theory, the network theory which is which we study, or circuit analysis which we study, is completely applicable only to lumped electric networks and is not applicable otherwise. See, we would not the objective is, even in case we are modeling transmission lines, the objective is to you know uh, lump it over an area so that the calculations are easier. And in electronics, it is essentially a lumped parametric system, right? Field theory, on the other hand, would be applicable to distributed parameters, right? So this was a general idea of what are the different kinds of elements that we are talking about. It is just a brief overview. It is not anything that we have discussed in detail. Also, because it is something which we will not be dealing with a lot. I do understand that you need to have a basic understanding of such elements, such topics, but for question solving and problem solving, you would not require a lot in-depth knowledge of such parameters. I would recommend you read your course books and textbooks. Just give it a one fresh reading, and that would enough. That would be enough. That would not, it would not hamper your progress in solving questions. From like such basic introduction would be enough for you guys. Now, uh, what are in now we're talking about energy sources, right? So energy sources can be classified as independent and dependent. So independent sources, and there would be dependent sources, right? So in independent sources, we have independent voltage source, we have independent current source, right? Again, everything, nothing in this world is ideal, but still, because we need to we do simulate ideal circuits for for a better understanding. So yes, a voltage source can be of two types, ideal and practical. Similarly, a current source can also be of two types, ideal and practical. Now, dependent voltage sources would be different kinds. What are the different kinds of dependent voltage sources? Voltage dependent voltage source, right? Then there would be uh, voltage dependent current source. Then there would be current dependent voltage source, and there would be something called as current dependent current source. Now just consider, like for a time being, just consider what are, just hear it for the sake of uh, knowing. You should know there are four kinds of dependent energy sources. Whenever we will deal with such questions, you would get a better understanding of what are different kind of dependent sources. Majorly, as whatever I've seen in your question papers in NET and CSIR NET, I do see a more frequency of questions on independent voltage and current sources, right? So now tell me, what is an independent voltage source? An independent voltage source would deliver energy to a network on its own. while a dependent voltage source would deliver energy from taking it from some other part of the network. See, I am drawing a hypothetical circuit. Right. So in network as shown, what is an independent voltage source? This voltage source is a independent voltage source, right? Because it is not dependent on any other parameter of the circuit for delivering energy. On the other hand, this voltage source is a voltage dependent current source. It is delivering current, right? This circuit, if you see, it is delivering current, but it is dependent on the voltage of this value of this resistance. So it is a voltage dependent current source. So it is dependent on some other part of the network for for delivering power, right? So this is a dependent voltage source and the current source, and this dependent energy source, and this would be an independent energy source. Now, what is a what is an ideal voltage source and what is a practical voltage source? Okay, okay. Now tell me, what is a ideal voltage source? So, in case, let us say, we have a voltage source such that we have a voltage source which is uh, which provides, you know, which is independent of the load, which would provide the same terminal voltage irrespective of the load resistance. So such a circuit would be an ideal voltage source. For example, in case the voltage source was, you know, which had some internal resistance, say small r, right? So, what would be the final voltage? In case the RL increases, what is the, what is the, voltage here? Let us say this would be the terminal voltage for this voltage source, right? This would be V, right? So, what is the terminal voltage at this place? VT. This is VT. Tell me, what is VT? So, V would be defined as VT equals V upon R plus RL. So if RL increases, VT would decrease. So the terminal voltage is a parameter of load resistance, and in such a case, this this source would not be a ideal voltage source because it has some internal impedance, and this is the practical voltage source, right? Similarly, you can define for uh, similarly we can say for ideal current source also. Ideal current source would have zero, this value, internal parallel value, right? Not zero, infinite value, right? And it could be independent of the load resistance. The value of the current, the current which is delivering would be independent of the load current. Otherwise, it would depend on the, in case it is practical, it would depend on the load resistance. So, All the independent sources are nonlinear in nature due to inherent nonlinear relation between voltage and current. They are basically nonlinear, active and unilateral elements, right? Also, we need to understand uh, very clearly that the current through a voltage source, for example, this is a voltage source. You cannot say it, that a voltage source is ideal voltage source is supposed to deliver energy. No, there can be, it can have any direction of current. It could be positive direction of current, it could be negative direction of current. For example, it could also, the current could enter through it, and probably there could be no current flowing through it. It completely depends on the nature of the network. So as long as this black box is not clear, you cannot comment on the nature of, you cannot say if the voltage source is ideal or not, just because the current is flowing through it or not flowing through it. You need to understand anything which is ideal in nature would have a constant terminal voltage or current characteristic, and this would be independent of the load. So it may deliver full current, it may deliver no current, or it may probably deliver negative current, but it can still be a ideal energy source, right? And this, I hope I'm being clear. So this would be your ideal case characteristic, right? If you're talking about a ideal voltage, a practical voltage source, okay? How would you define this practical source? It would be Vs minus I Rs. This would be your source resistance, right? This would be the characteristic of a practical voltage source. This is something which is very basic, and I do understand a lot of you would not even know, would wonder why we're discussing this. But just because we need to, consider this as an introductory lecture, right? Now, in case we have a circuitry with, where the net, there is no current flowing, then this and this would overlap, right? Because there would be no current flowing. So a practical voltage source is as good as an ideal voltage source only in one condition when no current is flowing. But that would definitely not make sense, because the objective of having a, you know voltage source would be to provide energy, right? Okay, so with this, I'll be wrapping almost everything which is theoretical. I will take your, questions on this subject, and probably for today we'll take just one question, and from tomorrow on we'll be taking more questions on the, on this topic. For today, I am just giving you a figure and try solving it. Okay, as the graph shows, we are having two scenarios here and two characteristics, right? We have two characteristics. I am defining this one to be y and this one to be x, right? And what I seek in this question is, okay, so in this network shown in figure, x and y are two practical sources. Okay, so x and y are two practical sources, and these characteristics defined by characteristics as shown. Vi characteristics are as shown. We need to determine the current I in the 1 ohm resistor. So we need to understand, this is something which is asked in the question. What is I in this resistance, right? So how would you approach this question? See, in given the curve y, how would you define y? Tell me. For y, how do we define definition? It is a straight line, so y is equals to mx plus c, right? So that would be, how would you define slope? 3 minus 0 upon 0 minus 3 times x plus the constant here would be, the y-intercept would be 3. So your equation becomes y is equals to minus 1 times x plus 3. So in other words, it would be, and in case we know they are practical sources, right? So when we know they are practical sources, we would understand, when we compare it with v is equals to vs minus isrs, what do we get? We get vs is equals to 3 volts, right? And rs is equals to 1 ohm, right? So the internal resistance of x, the net of this this is now determined, right? Right? Now we need to understand. Let me solve here. Okay. Now we for similarly for this, the other source, practical source x. How would you what would you get? 2 minus 0 upon 0 minus 4 times x plus 2 is equals to y. That would make Vs is equals to 2 volt, right? See, this would be y. And if we are comparing again it with the basic, this fundamental equation of a practical voltage source. So when we compare, we get Vs to be 2, Vs to be 2, right? This would be your Vs, and similarly your Is would be, rather your Rs would be, what would be your Rs? 1.1 by 2 ohm. So this would give us the internal resistance of this network, right? So now, in case we need to redraw the circuit, let me, in case we do, in case we do redraw the circuit, is it visible to rest of you? Okay. So when we redraw the circuit that was given, we could redraw it as 3 volts. This is for the voltage source that we calculated first. Now this would be 2 volt and this would be 0.5 ohms, right? And we were asked the current through the resistance of 1 ohm. This would give you current as, see, this is a very simple question. Only we were given two characteristics of practical sources, right? That was being asked for, and in this case, we calculated I to be 2 amperes. So this was a a very simple question wherein we were given a certain, uh, we were given, we were given two practical sources X and Y. We were asked the current through the resistance of 1 ohm, and the characteristics of X and Y were given through a graph. Now, if you see the slopes, we can clearly get the equations for these graphs, and when we get the equations, we can compare it with the basic equation of a practical source. We'll get the we'll get the the actual ideal voltage and the source resistance, and through that we can calculate the net resistance of the circuit, assuming the rest of the networks to be ideal. So this is kind of these are the kind of questions you would get on practical voltage sources, right? For today, let's end the lecture here. Tomorrow, I'll try and for saving time, I'll have questions written on your this whiteboard, so things would be easier for you. And we can also save time. From tomorrow on, we'll be doing more numericals. Nothing like we'll try and not divulge into a lot of theory, and we'll keep a lot of numericals so that you can understand how to approach questions. Once you're okay with approaching questions, we can probably take up parallel lectures on AC circuits or op amp, whatever you guys desire. Okay, so this is it for today. Let's meet tomorrow at the same time.